In this video, we'll talk about tensors. Previous video, we'll talk about vectors. Alright, so how vectors is gonna link to tensors, we're gonna talk about in this video. So in this video, I'll just simply talk about this section. Alright, the definition of the tensor and something later on. Alright, so next video, I'll talk about these things. So in this video, I'll concentrate on mainly on these stuffs. Alright. And therefore, in order to explain what is tensor, I'll just start off with something similar, familiar to you in the last video. Alright, this is the generalized form of a vector in 3D space. Alright, and take note that this v1, v2, and v3 are simply scalars, or in other words, they are the components. Alright, the components of the vectors. Or in other words, this whole thing is simply the components of a vector. So what builds up the vectors are these components. This is the meaning of that. I just want to lock it out more strongly. We often represent vectors, alright, v, often represents in terms of x1, x2, and x3. Right? However, in our context here, we would say that is v1, v2, v3. Alright? And therefore, this is simply stating this thing. Okay, this is just the meaning of that. Therefore, to lock on again, is that v1, v2, and v3 is not a vector. Alright, they are just scalars. They are just components of a vector. Alright, I hope that this is very clear now. To rewrite things in terms more simplified or perhaps clearer, okay, this is my pen over here. Okay, so I'll just state that v bar, underline bar, okay, this states that it's a vector. I'll say that this is v1 bar is equals to v1, v2, and v3. Alright, so we have another vector. I call it u bar. Alright, I call it u bar, or perhaps I don't call it v1 bar. Alright, I just call it v1. I just call it v. Alright, sorry. I don't know what the fuck am I talking. Anyway, so in this case, we have another vector u, underline bar. So this is a vector, u is a vector, v is a vector. Alright, let me remove this. Okay, so I'll just, instead of v, now we have u1, u2, and u3. So these are the components of u. These are the components of v. Alright? And e1 hat, e2 hat, and e3 hat are simply the basis vector. So I just want to repeat and repeat until you are very clear of what the hell are all this. Alright? If for example, if this v vector, alright, this v vector in the 3D space has a certain vector force, alright, and u itself has also another certain vector force, alright, and the relationship between them, alright, has somewhat a more profound meaning. So the relationship between them often are vectors multiplications, correct? Vectors multiplications. And therefore you cannot take v bar, alright, times u bar, alright, because it will simply be, which has not much of a meaning, alright, multiplications in terms of this is not. Alright, so if you feel that it's weird, then later on you'll know what I mean. So therefore, for normally multiplications of vectors, alright, v bar transpose multiplied by u bar is equals to your standard way of doing your dot product. Your dot product. Okay? So I'm not going to go into details, but I just want to let you know that v transpose u is equals to your dot product. And in these terms, this is considered one of the multiplications of tensors. Alright, I'm not going to go through it because later on we will go through it in the next few videos. But I just want to give you this concept first. Alright, of vtu is equals to v dot u. Alright, v transpose. But what if I have instead of V transpose U, I have V, alright, U transpose, alright. Then we're gonna have a what we call the 3 times 3 matrix. Okay, so if you want to go into like the rows and columns, so if you know that V transpose is actually it's rows times column, right? So we have 1 times 3, alright, and this is 3 times 1, and therefore in the dot product we have 1 times 1, correct? I hope that this is pretty clear. It's simply rows times column. The 1 times 3, the meaning of it is just V it's 1 column, alright, times normally rows times column, alright, n times m. Okay, so in this case this is in terms of 3 rows times 1 column, alright. If it's a transpose, which is V1, then this whole thing is equals to 1 row, right, because it's only 1 row, times 3 column, because 1, 2, 3 columns, alright. And this is just what I'm talking about, if you happen that you forgot, and therefore this is what I'm writing. So therefore this is 3 times 1 with 1 times 3. Alright, if you don't know, you can just write it out in the paper and you will eventually know. But I just want to convey that in this case, then you're talking about 3 times 3 matrices. Therefore, if you were to allow me to write it down in terms of V and U components, alright, so I have V1, V2, V3. Alright, this is the vector V, correct? And then I multiply with the vector U transpose. So I can just write the multiplication rule, alright? After writing, I have this one, and therefore this is the vector U transpose, okay? So if you were to do that, you're taking V1 times U1, alright? And therefore, instead of writing the U and V, alright, now I write a new so-called matrix. I call it W, alright. So W is a 3 times 3 matrix, alright, and the components are being described as W, because V1 times U1, so I'll just W11, alright, and then V1 times U2, so I'll have W12, alright, and then we have W13. So it's all this V1 in the X component, alright. If you were to look at the basis, or perhaps the axis, we have X, we have Y, we have Z. So if that's the case, then V1 is in terms of this direction. So all this row, first row, alright, it's all dependent on this X direction only, okay. Later on we'll have a video to show it out, so things will be somewhat clearer. And I will assume that you really know the outcome of the rest of the vectors. Alright, so I will have W33 over here. Alright, if I fill it out, okay, for simplicity's sake, so I'll just fill it out over here. And this is the familiar matrix that you often see. Okay, and therefore what is this meaning, alright, is that you can actually take a look at this video. Okay. So before starting this video, I'll just like to let you know that these cubes, alright, these boxes are called the components. Alright, these boxes are called the components, or in other words, it's called the V1, V2, and V3. Alright, some values. Alright, that stands upon something like a scalar. Alright, but in terms of components that we call. Okay, so I want to make it clear that this is the components. V1, V2, and V3, and that these little things are the unit vectors. So this stick, I would say, are all basis vectors, alright, which are the E1, E2, and E3. Alright, so based on this, then we can build on the higher level of tensors, and here you go.
To generalize this to vector capital A, for example, we can replace these components with a sub x, a sub y, and a sub z.
So we're just simply renaming the components as ax, ay, and az, alright? Something as our v1, v2, and v3, or u1, u2, and u3, okay?
Of course, a sub x is the component that pertains to the x hat basis vector. A sub y pertains to the y hat basis vector. A sub z pertains to the z hat basis vector. Notice that we need one index for each of these because there's only one directional indicator, that is one basis vector, per component. This is what makes vectors tensors of rank 1. One index, one basis vector per component.
So therefore one index, alright, x. So this is the indices x, y, and z are the indices, or the subscript x, y, and z, they are called indices. And therefore there's only one indices for only one component and one basis vector, and another one for one component and one basis vectors. So this is the indices it's talking about. And
by the same token, scalars can be considered to be tensors of rank 0, because scalars have no directional indicators, therefore need no indices. Those are tensors of rank 0. I'll say in a minute why it's so powerful to represent tensors as this combination of components and basis vectors. But first, I want to show you some examples of higher rank tensors. This is a representation of a rank 2 tensor in three-dimensional space.
And therefore this is the one that we just shown you earlier in the 3 times 3 system. Alright, this is the matrix. Is going to talk about it. So as you can see, we have two indices now. Alright, 1, 1, 1, 2. So for v1 we have only one indices, 2 and 3. Alright, so this is the indices that I want to introduce you to this also.
Notice that instead of having 3 components and 3 basis vectors, we now have 9 components and 9 sets of 2 basis vectors. Notice also that the components no longer have a single index, they have 2 indices. Why might you need such a representation? Consider, for example, the forces inside a solid object. Inside that object, you can imagine surfaces whose area vectors point in the x.
And therefore, in a 3D cube, alright, so you have some x, alright, x, y, and z surface area. This is what he's going to talk about, alright?
Or in the y, or in the z direction. And on each of those types of surface, there might be a force that has a component.
So in this x surface, alright, it has some components, alright, forces of the components acting on this plane.
In the x, or in the y, or in the z direction. So to fully characterize all the possible forces on all the possible surfaces, you need 9 components, each with 2 indices referring to 2 basis vectors.
Okay, so I hope that this is pretty clear. To represent things to a more clearer view, alright, imagine I have a cube, okay? So as he says, you have the area, alright, the surface area of x, of y, and of z, I would say, okay, for some reason, okay? And therefore, the surface area, in this case, the first index is 1, alright, this is 1. So there are a hell lot of 1, 2, and 3 acting on this surface, alright? So I would say that the forces of vectors u, alright, in u1 is acting on the surface area of v1, and therefore I would say that this is the I would say w11, sorry. So I have w13, w11, and w12, okay, based on their axis, alright, so it's somewhat like x, y, and z, okay, so 1 is x, y is 2, and z is 3. for example v1, v2 and v3 lah. Okay, so therefore in this plane, alright, I will say that in this x plane, alright, this explains all the three directional forces acting on this surface, alright, and therefore at this surface w2, which is the y surface, you'll have another axis, alright. As you can see, I have this w2, w3, w21 and w22. So this stuff is for this surface area, alright, and I will assume that you already know for this one is for this surface area. Okay, so I just want to end by just summarizing what you have learned. So we have talked about the definition of tensor. Okay, actually haven't yet, so let's talk about it. And therefore, by understanding all this, let's talk about scalar vectors and tensors. Alright, they are in fact ranks of tensors. So for scalars, it's just C is just some numbers, 5, 4, whatever, okay, some numbers. And therefore this is somewhat, I just write it as 3 to the power of 0, alright, which is 1. Okay, for vectors in a 3D space, alright, R3, okay, is simplified by v1, v2 and v3. These are the components, alright, as we said earlier, the components. And therefore we can represent them in terms of 3 to the power of 1, which is 3, right? As you can see, these are the indices 1, 2 and 3. So these are the indices. Okay, so there is actually 1 indices in each of this component. Alright, so there is 0 indices in this one component, and therefore 0. Okay, now let's talk about this one, the matrix itself. We have two indices in one component, alright, and therefore we have 3 to the power of 2, which is 9. And from here you can see, if I were to generalize equation, I can simply write as 3 to the power of what indices, how many indices do they have, alright. But strictly speaking, we'll use not equals, but rather we should use P, alright, the rank of the system. Okay, you determine the rank or order of the systems, alright. So we can also use indices as a way to actually, because if there is 2 indices, so we will just write 2, and therefore this is 3 to the square is 9. Alright, if it's only 1 indices, right, so we have just 3 over here. Alright, this is a very key important note over here. And the Y rank is because we want this row and this row and this row to be independent. Alright, they have to be independent, meaning they are all distinct, they are all not the same, and therefore at the end of the day we can arrive in this tensor definition. Alright, so tensor definitions is in terms of 3 to the power of number of the rank, independent rank, or you can say that the indices, provided that it's independent. Alright, so I haven't finished yet. So now, before ending this, let's take a look at why tensor is used in finite element analysis. Alright, so we can just get back to this video. You can just type tensors, and the first video you will come on is this one. Alright, this is a very good video, and therefore let's continue in this video.
This is a representation of a rank 3 tensor in 3-dimensional space. 27 components, each pertaining to one of 27 sets of 3 basis vectors. I'll zoom in a little bit here so you can see the components better. Notice that now each component has 3 indices. A sub xxx pertains to 3 x basis vectors.
Alright, so there is 3 indices, alright, so therefore if you were to use our formulas, alright, 3 to the power of the rank, so there is 3 indices in this case, and therefore 3 to the power of 3 is 27, and therefore this is why he said that there is 27. As you can see, you are breaking down the cube into 27 smaller little cubes. Alright, so this one cube signifies somewhat a small portion of the whole cube itself. Alright, if you were to remember in our matrix, Alright, and now this matrix over here, we have this cube that takes on this surface only, correct? This one surface. Alright. However, if you were to go to a rank 3 tensor, you're gonna dissect this little surface, alright? Or in other words, this blue color surface, alright? This surface, we're gonna dissect it into 9 more parts. Alright, so we can in finite element we analyze things in terms of infinitesimal, alright, meaning very small stuff, alright, or we break down into many elements to analyze, alright. So therefore we actually break them down into these little components and analyze them in terms of these little components, but depends on the applications. So if let's say this is a flat surface, then you can just analyze in terms of this matrix. If you have some surfaces, let's say this is the surface, alright, but you have some curvature over here, so you may use a higher level of tensors to analyze things. And therefore this is how the finite element comes about, and how tensors it's so useful in finite element, because you can dissect or you can break down this one cube or one solid into multiples of little smaller stuffs and analyze this little stuff individually, and then sum them up together to have a certain analysis or conclusions to the analysis, I would say. And therefore this is the answer for why tensors are so important for finite element. Therefore, to conclude this tensors video, in our video on tensors, we'll talk about this already. Alright, I hope that this and far more things than this. Alright, and next video we'll talk about this one. Alright, it's also still under the definitions of tensors. I will see you there.